Hello, everyone. My name is Andres Vázquez Quijano, and on behalf of the organizing committee, I would like to welcome you to the second edition of this workshop, Philosophical and Technological Reflections in Contemporary Cosmology. We are excited to see how this initiative has grown to reach not only a broader audience, but also attracting valuable contributions from colleagues of other countries. I'd like to thank the National Autonomous University of Mexico, the Institute for Philosophical Research, and both graduate programs in philosophy and philosophy of science, for they have provided not only this virtual space, but also the technical means to make it successful. I'd also like to thank the scientific committee, as they have provided very insightful assessment of the contributions to grant us a wonderful program for the following days. Um, that said, I'd like to introduce you to our first chair and also our first keynote speaker. So this is Atocha Liceda from UNAM and Axel de la Macorra from UNAM's Institute of Physics.
Okay, I guess I'm starting. I would like to thank Atocha Liceda, Andres Vasquez, and Maria del Rosario Martinez for this kind of invitation to give a talk in cosmology, and in particular on our experiment DESI, which is breaking paradigms, and where we have been measuring the cosmological constant, which in fact is not a constant, and breaking the stereotype of the last over 50 years, but not still expected from particle physics point of view. So here we have a glance of the universe. From the left side is very bright, and at the beginning of the universe, which you have absolutely no idea how it came up and why it has the amount of matter and galaxies and everything that we do have. And so we do not have any explanation whatsoever on this, but we can measure the expansion of the universe and the history of the universe until very early seconds and milliseconds of the universe. And in this path of understanding the universe, seeing the, I mean, we know that we cannot go to the past, but the past arrives to us, so we actually see the different stages of the life of the universe. And so we do actually see how it was way back in the past. And we know that in the beginning, there were basically elementary particles like electrons, protons, and neutrons. And at some point, there is a very interesting phase, which is called inflation, where the universe expands in an accelerated way. And this expansion was predicted from a theoretical point of view, because many years later, when we see the microwave background radiation, which is 375,000 years after the Big Bang, we see this print of light of different areas that were completely disconnected, and still they have the same temperature. The temperature of the CMB is basically 2.7 Fahrenheit, Kelvin grade, and the difference in the temperature of the microwave is around 10 to the minus 5. And in order to understand this homogeneity of the universe, cosmologists have come up with an idea of an inflation period in early times. So basically what we see in our universe comes from a very small bubble, which was thermalized and had basically the same conditions. And that's what we're actually seeing. Interesting, this inflation that we postulated at early time in the expansion rate, we see at 13,000 years later, we see another accelerated expansion. This time it's called dark energy, which dark energy basically only means that we have no clue whatsoever what is making this acceleration. Of course, different theoretical physicists have some ideas of what it could be. And in the beginning, I would say until very recently, the most common explanation for this acceleration of the universe was a cosmological constant, which was kind of proposed by Einstein in a completely different area. But a cosmological constant has been the standard model in cosmology, basically until the last year, where our experiment has measured a deviation from a cosmological constant. And I will explain you how we can actually measure it with such a precise data using only the distribution of galaxies and quasars in the universe. The first persons to measure basically the acceleration of the universe were back 20 years ago with the supernova, which are stars that explode, and the supernovas SN1A are basically have the same watts if we compare it to a bulb. And depending on how far we see it or how dim the light we see, it depends on the size, and we can measure also the expansion rate of the universe at a local region, and that supernova experiment measured the accelerated expansion of the universe. And so this is our telescope. It's in Tucson, Arizona. It's a telescope of 4 meters, which is a very small for astronomy. So it's well used now in cosmology. Astronomers go for 10 or 20 meters telescopes and not the 4 meters that we have in DESI. But since we do not care too much about understanding a single star, a single galaxy, but we want to measure millions of galaxies, this size of the telescope is excellent for our science that we are doing. On the left-hand side, we can see the different type of objects that we see in the universe. We will have around 3 million quasars. We can measure also the Lambda and Alpha Forest. Lambda and Alpha Forest, there are not stars, anything like that, but it's just like a cloud that absorbs Lambda and Alpha photons. And from this absorption, we can measure how much, how dense the universe is at that time. We measure the galaxies, which are called the Michelin galaxies, which are basically on a redshift between 0.6 and 1.6. Then we will measure 8 million luminous red galaxies, which these galaxies live in a redshift between 0.4 and 1. And then closer to us, we measure 13.5 million bright galaxies in a redshift close to us and a redshift to 0.4. So basically, we have measurements at different states and at different epochs of the universe. So a couple of very simple equations, which the expansion rate h, a is basically the radius of the universe, and a dot is just the derivative with respect to time, and the Hubble constant h is defined as the derivative between the scale factor. And general relativity tells us that this expansion rate of the universe depends on the density energy, the cosmological constant lambda, in this case would be just a cosmological constant, but that this can be changed into a dynamical dark energy, and the K corresponds to the one that is divided by by the scale factor to the square, is basically if the universe is flat or not. In most cases, we usually use a flat universe, which has been measured by the CMB, and we sometimes, we do study possible deviations to that. But the most standard cosmology at this point is assuming that the cosmological constant is 0 and we live in a flat universe. And in the universe, we have different kinds of particles, and we can basically constrain these particles into particles that have a mass, and if they're massive compared to their temperature, then they evolve as the scale factor A to the -3. If it's radiation, that basically means that the particles have an important thermal velocity, meaning also as well that the mass of these particles is very small, or could be even 0. In radiation, for example, we have the photons or neutrinos and some other possible relativistic particles. And then we have a cosmological constant, and if it's a cosmological constant, it doesn't evolve in time. However, as we will show later, the cosmological constant right now does evolve in time, so it's not a cosmological constant, but a dark energy, which is with a slow evolution of the universe. Depending on how it evolves, the universe, like matter, evolves as I2-3, radiation dilutes even faster, I2-4, dark energy is basically constant. And so the universe, the history of the universe is that we have early time radiation dominates the universe, then it transitions into a matter domination, and finally we end up in a dark energy domination at this stage. And dark energy, usually we use it in contrast to a cosmological constant. They try to describe the same thing. It's just that dark energy is not necessarily a constant, while a cosmological is, of course, a constant. And here we have the relative size, how it grows depending on how much matter and how much dark energy we have. So, for example, in red, we have, this is basically the standard model that we have right now, like a 30% of matter and a 70% of dark energy. And so we can see that this is going to grow faster in the future, which represents the right part of the graph. Then in blue, we have a model where we have 30% of matter and no cosmological constant. So we can see there's a huge difference in the evolution of the universe. And in green, we have a model where we have only matter and no cosmological constant. And the last one in orange, we have a huge amount of matter, 5 times larger than the one in green, and that one actually makes the universe to collapse. So the orange one is a universe that grows as it evolves, but at a certain point it starts shrinking again. That is very similar to as if we throw a stone on the air, it goes up a certain amount of meters, and then it comes back to us. That would be the orange one. The red one, which is basically the one that describes our universe, would say that the universe expands slowly, then it starts expanding faster and faster. And eventually, maybe we won't be able to see objects that we actually can see right now in the universe. So how can we measure the distances? How can we measure how the universe grows in time? And there are two different objects that allows us to determine this. The first one, which has been in the field over 20 years, which are supernova, here portrayed by candles. And so if this candle has exactly the same watts, and depending on what the luminosity we see, we know the distance to the candle. Those are the supernovae. And the supernovae usually are close to in time to where we are, so we cannot measure with supernovae very, very large distances. On the other hand, on the right-hand side, we have a ruler, and this ruler are the baryon acoustic oscillation, and we can measure this ruler at different distances from us. And due to the physics that comes out with the baryon acoustic oscillations, we know that this ruler is exactly the same size. And this is what our experiment DESI actually measures at different epochs. And we can go much farther in the past, measuring the expansion rate of the universe with the baryon acoustic oscillations than with the supernovae. And so here is a picture of a supernovae. We can see on the left-hand side, we see a arrow pointing to a point, and then at a moment later, we see a huge explosion. That's a supernovae. And so it's very, if the telescope is actually seeing it, it's a wonderful way of seeing the growth of the supernovae and explosion. So again, knowing what the luminosity of this explosion is, then we can know exactly what the distance to the supernova is. And the other one is the one that our experiment DESI does, which are called the baryon acoustic oscillations. And the origin of these baryon acoustic oscillations we see it on the right-hand side. Okay, on the left-hand side, what we're actually seeing is the microwave background radiation, and its different points. The difference in color is up to 1 in 10,000, and that's what a Planck satellite measured with a great precision. And we have like a standard ruler with a really, really good precision from the early universe. At that time, there were, again, no stars, no galaxies, no nothing. It was only light, electron, protons, photons, and elementary particles like that. On the right-hand side, this pattern from the left-hand side, where we see different colors means different temperatures, translate on the distribution of the galaxies that we see today. And this time, we don't see it necessarily only on the radiation, but on the galaxies, how they are distributed in the universe. And so this is really interesting to be able to correlate these anisotropies that we see at early universe with the anisotropies that we see at a universe close to our present time. And so what are these acoustic oscillations? So we can see on the right up part of this slide, we see the CMB, the microwave background radiation, which is only light at a redshift around 1,100, which is when the atoms formed. And then we have two other slides at a redshift closer to us, which is 2.5 and redshift 0.5. And the circles that we see in the light many, many thousands of years ago translate into a distribution of galaxies at a later stage. And we can see it in the intergalactic medium, which is a redshift 2.5, and the distribution of galaxies at a much closer time, for example, redshift 0.5. And we can see on the bottom part, on the right-hand side, the measurements of this distribution on the horizontal scale. We have distance. On the vertical scale, we have also the density, the amount of density that we observe at that stage, also at the distance. So what we actually see is that the more the curve goes to the right, is decreasing, basically because the area and the amount of objects is decreasing. But we see an excess around 110, 120 parsecs. This peak is exactly related to the baryon acoustic oscillations, and this peak tell us a lot about how the universe evolves. And so let me show you just experiment. This is a Mayo telescope, Kitt Peak in Arizona, which is by it's a rather small telescope by the telescopes that they are one measuring. So we want to see a single star or pinpoint out a galaxy. This telescope is not very good, but I mean, in cosmology, we don't really care about the tiny details of these objects. We care about having a large amount, having a map, a three-dimensional map, as precise as possible, and it works very, very, very well, this experiment. In order to measure a lot of galaxies and measuring the redshift, redshift again means is the light that we receive, and the redshift from a different objects can have different wavelengths. So depending on the velocity, the relative velocity of the object that is emitting the light and we are observing it, this pattern of light can be shifted to the right, and this means that the object that is emitting the light is receding, is moving away from us, and we can actually determine exactly what the speed is from that. So when we make this three-dimensional map of the universe, what we actually have is two angles to pinpoint where the galaxy is, and then the redshift, which basically means the receding velocity in comparison with us. So we have one velocity and two angles. We can see, I don't know if you can see my pointer, probably not. So on the left, there is you can see a fiber, which is a tiny, tiny thing there in the instrument on the left-hand side. Below this picture, we can see many fibers stuck together, and then there is we can direct it. So from the right-hand side, you can see that this robot is moving, and there is a filament, which is a fiber, and that's actually what takes the picture. And we have so we have 5,000 of these instruments looking into the sky at every moment. And this is, for example, the footstep of the telescope. What you see in blue and the points are the different fibers looking into the sky, and this they are showing exactly what we can actually measure. The different emission lines of this galaxy, and this was the first light taken back in 2019. That was the first light that our experiment measured. And this is the instrument, this is the focal plane. And you can see probably some points which each of these points have a fiber. Let me just show it. So each of these robots that are moving, they have a fiber. The fiber is like a white, it's in white color. And the instrument, all these positioners are just moving so that the fiber takes the light from the galaxy that we are supposed to measure. And since we have 5,000 of these ones, then we can at each moment take 5,000 pictures. These pictures, as I mentioned before, take 20 minutes to because the light is so faint that it is necessary to have 20 minutes observing the different galaxies. Still, every 20 minutes we have 5,000, a map of 5,000 galaxies. And if you repeat this every night, 8 hours every night, you come up with millions of galaxies after some time. This is just a slide of the measurements of our experiment. All the colors and the position of these galaxies are real. And there is a fly-through just by the instrument. The galaxies do not move like that. It's just like if you were in a spaceship moving into these galaxies. And this is just a tiny, tiny part of the universe that we have measured. Okay, and so this is kind of a map of the measurements that we are having. Here we see only a slide. With SDSS is the experiment previous to DESI, what they actually measured until redshift around Z equals 0.7. Now we can measure things until redshift Z 4, and galaxies started appearing around redshift Z equal 2. And so here in this picture, this also the picture is a slide of the observations that we have done in with our experiment, and we can see the different what we're going to measure. The luminous red galaxy LRGs, we're going to measure around 4 million of them. The elongated galaxies, we will have around 17.1 million of these objects. The quasars as traces, the measurement of the quasars is 1.7 million, and then the quasars in Lambda and Alpha, which means that we measure the path of the light that is traveling. Quasars are the objects that emit light which are the farthest away, and so it is interesting to know where they are and what they are, which is not entirely clear. But in its path, since there may be clouds of particles, they can absorb and they can interact with these clouds, which are in between the quasars and us, and so we can actually measure the clouds that are in between these distant objects and us, and so we kind of know where in the future there will be more galaxies and stars forming. And so that's actually very exciting. So the total objects that we're going to measure in dark time basically is when the sky, when the moon is not illuminating to bright the sky, around 24 million galaxies. And in the bright galaxies, which is it will be around 10 million. That was the objective of DESI. However, our experiment has exceeded the forecast. So I think we are going to make sure around 25% more than of what it was proposed. And so from the distribution of galaxies, we have two different models. One has 70% dark energy and 30% matter, which is the blue one on the left-hand side. And the other one is just a 100% matter. This is just an example. And these are what they are called a position of galaxies from n-body simulations. And the A is the scale factor, so A 1/4 is before then A 1/2 and A equal to as today, and you go back in the past. And so we can see how we expect the universe evolves at different times due to gravity. And we can see clearly that these two different models, one with 70% dark energy and the other one with 100% matter, the distribution of the galaxies is very, very, very different. So we can actually determine quite precisely from what we see, what we measure from the universe, and then forecast what is throwing this expansion rate of the universe. And that's exactly how we have measured the expansion rate and the equation of state of dark energy. Once again, here is a list of the amount of galaxies that we're measuring. DR1 is the data release 1, and DR2 is data release 2, which is where we are. We're going to measure much more, but this is the state of the art at this point between the different objects, tracers, bright galaxy survey, luminous bright galaxies, elongated galaxies, quasars, etc. And so let me just show you what is the distribution of the galaxies is correlated to the time where the atoms formed. And so we can see in this graph that we have right now that we have dark matter, gas, photon, neutrinos, and they are all concentrated basically at a distance 2 of megaparsecs. If we evolve it with time, what happens is that due to the pressure, these particles will try to fly away, and we have 3 different particles, the neutrinos, which do not interact strongly with neither the photons and dark matter, which is in green, will fly away. I mean, they are concentrated and just distribute. Then in red and blue, we have a gas, which basically means, in this case, protons, and the photons, due to the protons and photons and electrons interact due to electromagnetic force, so they are bound together. And in the center, on black is dark matter, where the majority of the gravity was, and that stays in the origin. And so we can see that these particles evolve from the center, and then at one point the gas, the protons and the photon decouple because the interaction is no longer strong enough to hold together, and so the photons fly away, and the gas, which are the protons, don't stream away with the photons, and we end up with a distribution of matter, in this case of gas and dark matter, basically of protons and dark matter, which is centered at the beginning of the radius here, which was the center, and then at a certain distance which is around 150 megaparsecs. And so this is the distribution of these particles way before there are stars and satellites and structure. And so still what we would expect after that is that whatever is going to form will be centered either in the first peak on the left-hand side around 10 megaparsecs and at a different distance, which is 150 megaparsecs. That the prediction of the baryon acoustic oscillation. That's a theoretical prediction. And so this is more or less a picture of what we see in the universe. This is a lake with some bubbles coming up, and we can see the circles, and there's circles all over the place. And so there is a mix of the circles, and that's similar to what we're actually seeing in the universe, just by analogy of this lake first. And here is an explanation of what the baryon acoustic oscillation is. We have in the center a concentration of electron, protons, and photons, and then due to the pressure, it flies away, and if we enter in a position, let me stop it here. Let me, okay, so we have different distributions of these galaxies all over the universe, and so if we see them when they're kind of mixing up, it's very difficult to actually see the pattern in of the galaxies. So a simple eye, we wouldn't see it, but if we make a correlation function between each of the galaxies all against all, and measure the frequency and due to the separation as well. So this is kind of what we see in the universe, and we're measuring the distances every galaxy against any other galaxy, which is called the two-point correlation function. And so we measure all of them. What we will end up is with a pattern where most of the galaxies are centered on the left-hand side, the peak, and then there is over density. There was an over density on the right-hand side. Okay, here we can see it. There's an over density in the center of the galaxies, and there is another over density at a certain separation, which is basically the same in all directions of the universe. And this distance tells us exactly a lot about cosmology, and this is what actually DESI measures. So these two separations actually what is a circle of galaxies in the center, and there is a sphere of galaxies outside. And so here on the right-hand side, we can see it. We have an overdensity of galaxies in the center, and then we have a sphere of around 150 megaparsecs, and that for all of them. And so we can actually, we of course we don't see it as simple as that in this picture, but we make a correlation function of the measurements of the position of the galaxy. We arrive exactly at this particular distance of the size of the sphere. And interesting, this size of the sphere depends on the epoch of the university. This size of the spheres, since the spheres start grow in time, so if they are closer to us, the sphere is larger than a sphere that we see, which is farther away than the closer one. And so on the left-hand side, we measure these anisotropies in the microwave background radiation, which is in green and blue, where there are no stars, there is only electrons and protons, but we see the other densities. These other densities get imprinted in the evolution of the universe. They form stars and galaxies, and the distribution of the galaxies corresponds to the initial distribution of the CMB perturbations. Once again, on the left-hand side, we have these spheres that we measure with the distribution of galaxies. On the right-hand side is the equivalent, but due to the light. This is the Fourier transformation. That's why we see all these wiggles, but it would be basically a single distance. And once again, here on the left-hand side, we have the microwave background radiation on the of the CMB in green and yellow, and then we see the galaxies at different stages evolving, and the sphere of these galaxies, the distribution of these balloons of galaxies grows in time. And so these spheres, which measure depend on basically the distance, which is dm is basically 1/h, an integral, and the other one is basically the Hubble parameter. So we measure the distance transversal and longitudinal to determine the spheres of the galaxies. And these are the parameters that are actually used to measure the baryon acoustic oscillations. Basically, once again, it's just the Hubble constant, how it evolves with redshift, and the distance dm and dh, which is basically an integral of the Hubble constant. So basically, the Hubble constant gives you all the information on how these galaxies and these spheres of galaxies grow in time. And here are the main results. In lambda colored matter model corresponds to a model where the cosmological constant is constant, which is was at some point predicted or by Einstein. And then CDM goes for cold dark matter, which is basically then we have the particles of the standard model. There is a dark matter which is cold. Basically, the particles do not have a high temperature. They don't move. And lambda is a cosmological constant. It doesn't evolve in time. And we're going to see what the peaks, as I mentioned, corresponds to the measurements of Daisy at different times. We see on the left-hand side there is a redshift from 0 to 2.5, and we have these distances, which basically the graph is the distribution of the galaxies, and the peak means is whether you have more galaxies in these spheres. And so we move to the right at different redshifts. That means different distances to us. And all of them have basically a similar distribution. We see the peak, and we see what the information gives us when we plot the amount of matter against the H naught and the radius, the original radius of these spheres. And we can see that all of them actually come up with at a value of omega matter of around 0.29 and H naught of around 101. And so all these different galaxies, which are at different distances, are consistent at those values. That's the measurement of DESI. Here is again a different measurement of DESI of different points in different quantities, dV and dm, and still they are all absolutely consistent with each other, and allows to determine how the expansion rate of the universe is. Here is the same as basically different ways of portraying the same thing, but it gives you a little bit more information, but still is the different sizes of these spheres at different times. And so here are the results of the first data release, DR1, and we can compare this to the data release DR2, which was this spring, and so there's a small change. And so now let us go into dark energy beyond lambda cold dark matter. So lambda cold dark matter, lambda once again is a cosmological concept. It basically means it doesn't evolve in time. And so what DESI did, which was proposed many years ago, but no experiment had measured or used a model different than lambda cold dark matter to measure the evolution of the universe in such a precise way. And I think it's interesting to note, and especially here, is that if you have the data and you don't have a proper theoretical model that may allow you to distinguish one model from the other one, either because it's too simple or because it's too complicated and you have so many parameters that you cannot fix it at all, that you will end up with basically no information. The simple thing with this evolution of the equation of state, that is WA equal to W0, which is constant, which is the value at present time. WA is another value which corresponds to the first derivative at present time. So it's probably just a Taylor series expansion at first order. There's nothing simpler than that. But at least if we measure that WA is different than 0, then we can rule out a cosmological constant. And so maybe this, or surely this expression of W0 plus WA 1 minus I is just an approximation. Still, if we measure that WA is different than 0, then we're ruling out a cosmological constant. So we're ruling out Einstein's model of the universe. And so here we have graphs of WA and W0. The cosmological constants, once again, is when W0 is -1 and WA is 0. And here are the observations. For DESI DR1 is the first data release, that DR2 is the recent release. And depending on what you're measuring, or which traces, or which galaxy you're measuring, you get different possibilities. So what we see in this picture is that within 2 sigmas is consistent with a cosmological constant. And if we go to, if we add a C and B, then the cosmological constant is no longer within the 2 sigmas. And when we use DO2 with the C and B, again, DO2 basically means we have many more galaxies than DO1. Then not even at a second, at 95% confidence level, the cosmological constant is consistent with the observations. And if we add not only DESI measurements plus the macro background radiation, but also supernovae, in this case, Pantheon plus, then we can actually see that at 95% confidence level, the cosmological constant is definitely ruled out as a model. If we use, instead of Pantheon as the supernovas data, but the union 3, we get the orange graph, which goes even further away from the cosmological constant. And instead of the supernovas, union 3 and Pantheon, we use the DESI 5, which are the newest supernova data. Is consistent with the 3 of them, but all of them are not consistent with a cosmological constant. This is really important. I mean, it's not only it's moving, it's just from a theoretical and philosophical point of view, is ruling out the model, which is a cosmological constant, which has been with us over 100 years. Of course, I would say, I mean, DESI. I mean, we're confident that the results in DESI are valid, but still, in order to convince the whole community, we would need another experiment different than this one to confirm the results that we are getting right now. Here are the evolution of the masses of the neutrinos compared to the Hubble constant or the value of Hubble constant at present time. And here we have there is a contradiction, or there is a tension of the CMB measurements and the SHUS measurements. SHUS are some supernova that explode at high redshift, and they go for a value of H0 which is around 72 to 74, which is way larger than the CMB, which is between 66 and 68. So this is DESI with Big Bang nucleosynthesis. This is DESI with Big Bang nucleosynthesis and the angle theta, which is well measured by CMB as well. And so still there is a tension with the supernovae measurements in cosmology, which is, I would say, rather interesting, because any tension has to be explained, and it always comes with interesting innovations. But still, so at this point, people would have to vote if they prefer the new baryon acoustic oscillations from DESI or the experiments or SHUS, or try to come up with a new theory that would manage to make these both experiments consistent. I don't know how much time do I still have?
Well, you are just 50 minutes right now, so it's okay. You take 5 more minutes.
Okay, let me just present you a model that we've been working, which corresponds to a dark gauge group. Basically, all the particles of the standard model corresponds to the gauge groups SU3, SU2, and U1. That's and 3 families. This is the standard model, which is probably the most precise theory in an experiment. And so what we introduce is another group, an SU3, but supersymmetric. So it's very similar to the ones that we have in the standard model. And in this model, we have that the force, the strength of the interaction becomes strong and forms in QCD the pions and protons and neutrons at a scale of 200 MeVs. And in our dark energy model, we also have the equivalent meson like pions, but dark pions. However, the scale is at a much later stage, around 40 electron volts. And so the standard model, the choices of the gauge groups are SU3, SU2, SU1, which are the interactions. It has 3 families. We have no idea why those gauge groups are, neither why there are 3 families. Still, that's the model and it works fine. So we use gauge coupling unification. If we evolve the gauge coupling couplings of the standard model particles, that is at different energy. We know that they become around 10 to the 16 GeV. They have the same value. So this is what is called a unification, that at one point these three interactions were a single one, and then they move into the three ones that we know. So if we assume that these three interactions are also unified with the one we have been proposing, which is another SU3, which is in red, the dark energy, we can determine the at what point these particles bound together. In QCD is 210 MeVs. In our model is a little bit later, 34 electron volts. And here, well, the evolution of the equation of state. So I'm not going to go through this, but these are the graphs of these two parameters, WA and W0, and we can do the same thing in our experiment, determine these two parameters, which we have on the right-hand side. And we actually see that we have a very, very tiny contour, which is on the left-hand side, compared to the ones that the W0WA model predicts. And interesting, this evolution allows us to understand much better the evolution of the model, the phenomenological model that is used by DESI, and it has a solid theoretical background due to because it's giving in terms of the gauge interactions as the standard model, as the SU1, SU2, SU3, which corresponds to the electromagnetic weak and strong interaction. So here are just some contour plots between the different models, BD in blue, lambda cold dark matter in red, and W0WA model in orange. And as you can see, interesting, and once again, in the plot between the two variables of the dynamics of dark energy, our model has a very, very small contour, and still is better, has a better fit than the W0WA model that DESI is using at current time. And so basically, just to conclude, DESI has measured with great precision the expansion history of the universe by measuring the varying acoustic oscillations at different times, basically redshifts. DESI measures a dynamical dark energy, ruling out a cosmological constant at more than 95% confidence level, opening the door for new physics. We have proposed a dynamical dark energy, bound dark energy, contained in a group as SU3 with the same formalism as the standard model particle gauge groups. Our model has no free parameters and has an excellent chi-square, even smaller than one in W0W cold dark matter. So what I want to finalize, I would like to say that cosmology is right now a very, very interesting subject to work on. There are plenty of open questions. There are many experiments coming with new data that will allow us in the next 5, 10, 15 years to answer with a much more precision all these questions that we can ask at this point. And so it's a moving subject, even though it's one of the areas of knowledge which has been with us by millennia of years. Each population everywhere in the world wants to understand the universe, and fortunately we have now the tools to try to answer questions that were only philosophical at some point. Well, I thank you for the invitation, and I will finish this.
Thank you, Axel. It was a wonderful talk. Before we proceed to questions, I have two issues to say. First of all, Axel and the audience, I apologize because I was somehow in a slow reaction to give even a short presentation of our speaker. I'm glad, however, that that happened because I thought that DESI, this acronym for the Dark Energy Spectroscopic Instrument, I thought it was the acronym of a project that you mentioned here in your homepage that says, well, Axel, he is really our local cosmologist. He's a physicist by training from the School of Science. I am glad to say that we met when we were students there. I was doing mathematics. And I am so glad, Axel, that you accepted for the second time to be in this event. If only because I remember very well that last year you were surprised that we philosophers were just asking so many questions. So I'm glad you're back. But in any case, I would like now to move to some practical issues. And the practical issues are that don't forget that you can write your questions in the chat, and also for the people who are following us in Facebook or in YouTube, feel free to ask your questions. In fact, don't hesitate to do it because Axel, you made the impression, at least in myself, that we understood something. So thanks very much for explaining to us how DESI works and your own model and all the antecedents and all that. And as Maria, one of the organizers, said, if you want to phrase a question, please raise your hand. I'm talking about the people in Zoom. And Andres has one. I have another one. Oh, great. So Sergio, Beatriz, and Andres. Andres, if you don't mind, let me... oh, no, that's not a question. Only Beatriz and Sergio said, like, great. Please, Andres, phrase your question and let's move on.
Hi, Doctor. It's nice to see you here again. My question is it sufficient with consistency to have a new model? I mean, consistency with the accepted physics?
Probably not. What I would say, it's very difficult to confirm any model. It's very easy to rule out a model. And I think what we have done so far with DESI is ruling a cosmological constant. And since the cosmological constant has been for 100 years, this is a huge result. And probably once again, I mean, probably the data were there 10, 15 years ago. It's just people doing the experiment did not ask the right questions to get the right answer. So they were always modeling lambda colored matter, so a cosmological constant, and all the results were to confirming a cosmological constant, which basically is very close to the result. It could well be that it's a cosmological constant, but they never asked the question. They never tested models beyond lambda colored matter, beyond a cosmological constant. And if you work with many astrophysicists and even some cosmologists that I know well, but they are from, I would say, there was no inclination to go outside of a cosmological constant and I would remain saying probably when the observations are complicated, they probably try to use it the simplest models, because the observations become so complicated, and otherwise you would not be able to say much. Still, it's always good to try it, whether you get results or not, and look for beyond the box.
Thank you, Axel. I misplaced Maria that made the question at 10:37. So I will read it aloud before Maximiliano phrases his question. Maria Pia Piccolini says, hello, Axel. Very nice talk. Thank you. Question. What do you mean when you say your model has no free parameters? Not even the ones that LCDM has? Thank you.
Oh, that's a really, really interesting question. No, in fact, no, because, well, we pick a model. So we assume that it's a supersymmetric NC equals 3 and NF equals 6 flavors. So that is a choice of model. Those are no, this is how many particles you have there. And so if this is no fine tuning, it's just saying this is the model, and then there is no free parameters to adjust. For me, a free parameter is I don't know what the measurements of this is, and then it changes. This is just different models will explain different things. So once you give this model, it has no free parameters. Of course, this model can be wrong, and then one would have to look for other models. But the main point, probably the interesting part that you can actually do in order to reduce the parameters is using gauge coupling unification. So basically, this is the unification of the couplings of the standard model particle physics. And so within evolution of a gauge group, instead of being free in our model, we assume the value of this conjunction of the parameters. And therefore, we import these values, we use it, and so it's not a free parameter in this sense. It's our choice to take that, but it's not a free parameter. We are not moving it. So this is a graph. So we have our model is the blue one. These are the evolution of the dark energy SU2 and SU1, and they in a gauge coupling unification they go to a point. And so, yeah.
Thank you.
Mm-hmm.
Now we move to Maximiliano's question. Please, Maximiliano.
Okay. Thank you, Axel, for the talk. My question is about the discrepancy in the parameters cosmological, in the constant cosmological. What do you think about for the one hand, the measurement of DAO, and for the other hand, the supernovae methods? This discrepancy, what do you think about the recent idea that the discrepancy is solved by the hypothesis that the Milky Way is in the gigantic local void that explain this discrepancy? What do you think about that?
Yeah, it's a very interesting question, and definitely there may be many different systematics and local positions that can change all the results. I haven't really looked into that. If it's very local one, then it shouldn't affect very much. I mean, because we're measuring this is way long, and so it would be small, the discrepancy. But yes, I mean, there are lots of things out there that could be important and that we don't really know yet. So I would say if you want to put all the possible free parameters, important things that impact your model, we will never get anything. So we have to probably start from the simplest, which is lambda cold dark matter. And thanks to lambda cold dark matter, we have, and yeah, I mean, if you see someone like Carlos Frank, that was, well, he's a very important scientist in the UK, as cosmology started kind of here. He's Mexican, and he believed very much in lambda cold dark matter, which was a model he started with, etc. No, and so you get constrained, or you get close to the to what you have, and you have to get a contradiction in order probably to move to the next model. This one here that what I'm showing, again, forget about the names, is this, it's just a Taylor series at first level. And in that sense, is the simplest possibility of testing whether cosmological constant it's impossible to test a cosmological constant if you don't go outside the box. So within lambda cold dark matter, there's no way you can say this model is correct or not, I would say. I mean, maybe if it screws up completely, you say, yeah, it's not. But if it's very close, it's difficult to not, yeah, I mean, that once you go a little bit outside the model, and this idea of having W0, W8, which is just cell expansion at first order, and you get the value of W8, which is not zero, tells you that there is some dynamics. Surely this equation will not be the ideal equation. It's just the important thing is W zero or not? If it's not zero, then there's something more. There's a dynamical dark energy. Which one it is, who knows? But it's then up to us to try to come up with the best possible idea. Then once you have a model, you get the results of this model, and they may be good or not, which is what bound dark energy model is. But there may be many models, different models that would probably be better than the one I've been working with, and that's fine. It's just I would like to see one. And so it's good because it's a moving in science. It's I think it will keep us working for a long time with many more experiments, and maybe the final cosmological model will be quite different, and I welcome that. That would be interesting.
Wonderful. Now we have a question by Sergio. If you want to appear, it's okay. If not, just talk, please.
Yep, thank you very much. Do you hear me well?
Yes.
Yeah.
Yes, we do.
Great. Well, first of all, thank you, Axel, for the keynote. I'm very glad to see again you all. I was in the last year workshop, so I'm very glad to be here too. Axel, I have two questions. First one is about the bound dark energy. So I understand that dark energy is something that it is there. It is making some changes, to say so, in the universe, but we don't know what it actually is. So my question is, if I understood well, if bound dark energy states that the dark energy may be something, and this something is these particles from the standard model. That's the first question. And the second one is, you say something like, if we have the data, but we do not have a model, we do not have information, right? So my question is, would you say that science interprets data? Is science is the way of how science works is interpreting something? Thank you very much.
Yeah, I think there are two questions. Probably I will start with the second one. I think the question should be for the philosophers here in our group to answer your question. What I do think is, if you have no model to test or to predict something, you have no possibility of knowing whether it's good or not. It doesn't really matter whether it's a really nice model that's beautiful, mathematically fantastic, but if you don't test it to anything, that's wishful thinking. And so you have to test it. And to test the model, what DeFi has been doing is, with this model W0WA, which is just a stereo expansion to first order, is I have no model, but let me just understand if the equation of state is constant or not. And the simplicity of that model, that I think it was in the data before, probably Sloan 10 years ago. If you look into the data that we had, they would have come up probably with the same result. But the question wasn't asked. And so you need to have a model in order to a model that contains the previous model but goes beyond it. And if the data, if the parameters of beyond the previous model are non-zero, then you would say, well, there is something more to it. And in practical terms, mathematical terms, it's just one extra parameter or not. And then if that parameter is zero or doesn't really matter, it could be any value, then you say, well, it doesn't constrain the value, no? In our group, I mean, the model that portray here is basically QCD, the strong force. The strong force has a SU3 gauge group with 6 flavors. The only difference is that in my model, I assume that this gauge group has supersymmetry and allows me to form the dark mesons and dark variance, and I can derive how it evolves. And then it of course it has many particles, this group, but usually, as it happens in the standard model where you have lots of particles, you can see that in the tables you have 100 even more particles. When they cool down, the particles, they all move into the lightest particles, and so the interactions always go to the lightest particles, and that if they're allowed to, they go. Is the way of life. If you have enough energy, then you can produce each way. But I mean, if not, it's just a decay. And so I would say in our bound energy group, I choose the group and the number of particles there are, flavors, which is very similar to QCD. It's only supersymmetric. And then I derive the evolution of the lightest scalar field using what is called Affleck-Dine-Seiberg superpotential. And so, yeah, there is a derivation there. The choice of the group is mine, in the sense that it's my choice, but it's not derived from anything.
Okay. So now we move to the Facebook question. I'm afraid I cannot tell who in particular is phrasing this, but I can already say it's very interesting. It says, at what point does it stop making sense to call, sorry, I don't know the name of this symbol, the sort of the upside triangle.
Lambda.
Of course, lambda, a cosmological constant. Is this mainly a terminological issue? Or do you think the conceptual role lambda has played in cosmology is fundamentally changing? This is a very philosophical question.
Yeah, I think The equations of Einstein, I mean, Einstein even proposed a cosmological constant because it was consistent with all the symmetries of general relativity. So you cannot add in general relativity whatever you want, because there are symmetries that you don't want to destroy all the symmetries that they have, like the transformation of the coordinates, etc. And so cosmological constant was consistent with all the mathematical theorems of general relativity, and that's why it was there. And then Einstein didn't like it because there was no evidence of that. And then when we start seeing that the universe not only expands, but expands in an acceleration way, and we had the possibility of measuring the amount of this new thing and how it evolves, it seems that it evolves very close to a cosmological constant. Basically, it doesn't evolve at all. With more precise measurements, particularly DESI, then DESI didn't prefer not to look into its particular models, but say, let's just ask if it evolves or not in time. And once again, having the evolution of W0 WA, the equation of state W0 WA is the simplest one that you can have. So it's just two parameters. You don't know what it is. If it's a cosmological constant, then WA is 0. So you have two parameters. It's just, can it evolve or not? And what we see with this is that it evolves. So that a cosmological constant is still consistent with what we see, the answer is no. There is something beyond that. What is beyond that? We don't know. Do we need to change the whole model? Probably. Do we need to change general relativity? Probably not. And so just to measure the dynamics, the simple ansatz, obviously WA is the simplest one, and it convinces everyone. It's just, we don't know what it is. If WA is different than 0, then there is an evolution. And I think it's the conclusion. I think it will remain. I don't see it going back, but I wouldn't bet my life on that.
Thank you. I know we have another question Victor wants to ask again. However, let me now introduce my own question because it's a follow-up of the previous one, and I want to push you into this thing. Okay, it's clear we're not talking about a constant in the sense of a number which is a result of calculating a equation. However, in your graphic, if I can call it that way, it's not a constant, but it's not the other extreme. It's not like a random thing. There is a pattern there. Would you say that it's not a constant, but it somehow approximates or converges into a constant? Would you where is the constant in not in this equation, but conceptually? Because you see it's not a constant, okay, but still the constant plays a role in your model. So my question is, you said we don't know exactly what it is, but conceptually, are we talking about some kind of pattern or approximation?
There are two things. One is this equation that we're seeing now.
Yes.
And what is my model? They're completely different things. This is what DESI uses to extract the evolution of the equation of state. So the question is, is the cosmological constant, or does it evolve in time?
Okay.
And if it evolves in time, so I need to have I cannot ask the universe, what is it? No, so you test the simplest model. And this one here is the simplest model where WA is different than 0. The WA is 0, then what you have is W naught and could be -1 or could be a constant close to -1. So I would say this statement here is not a model, it's just a Taylor expansion to first order. And if the value of WA is different than 0, then a cosmological constant, I would say, is ruled out. You can never prove something is correct. You cannot, but you can rule out things.
Okay, so Victor, could you phrase your question very quickly, and perhaps Axel can answer in
Yeah.
1 second.
15 seconds. Thank you.
Sure. Well, since the standard model of particle physics doesn't currently account of dark energy, would a time-varying density suggest the existence of new scalar field? And if so, how would be even been to integrate this field into our current particle physics framework?
Well, yeah, my model is precisely having it's another gauge group, and it has different particles, and it has scalar fields. In order to impact the expansion rate with an equation of state, yes, you need scalar fields. These are the so you can either postulate I have a scalar field and that's it, and you need a potential as well, so you can choose any potential that you want, and that's more or less what people kind of do, having a scalar field and potential, and you test different potential and see how it works. For example, in the model that I propose here, I can derive the potential and I test it. So it's not on my choice. My choice is the gauge group, and then the evolution of the dark energy and the potential is given by this by group. But I mean, it's a complicated derivation that is I didn't wrote the equations. No, I don't know if I answered your question, Victor.
Yeah, thank you.
Okay, wonderful. So let's thank our keynote speaker, Axel de la Macorra. Thank you so much. And now you guys just have to switch because it's Victor Eduardo Garcia talk, and I stop being the chair, I guess.
Okay, I just want to thank Maria and you, Atocha, for inviting me to give this talk here. Thank you.
And Andres Vasquez as well, yes.
Yeah, and Andres Vasquez, sorry, yes. I will stop sharing.
Muchas gracias, Axel. And thank you very much for inviting me to the scientific committee and to chair this session. Maria and Andres and Ana Rosa Perez Ranzan, she was also organizer. So thank you.